Hello, fourth hour HansenMATH students. This is going to be the continuity learning plan assignment number 2 for our fourth hour Algebra 2 class. The majority of the class already turned in assignment number 1, which is great. That was Google Forms style, fill in the blank, if you will. This lesson is going to be one where you're going to want to use paper and pencil. And when it comes time for the assignment portion, you're going to want to write it down on a sheet of paper, or you can print, if you have a printer, that's optional. You could print my attached graph paper, but at any rate, you're going to want to write it out and take a photo of it and upload that to Google Classroom. So we're going to try a little bit different today. So without further ado, let's get into lesson number 2. And again, you need paper and pencil. You may want to use a calculator. I want you to take 3 examples of notes with me, and then we'll get a move on. This assignment should not take super long. And here we go. Make sure you have your paper and pencil ready. You're going to hear something called the unit circle. The unit circle is an important tool that's used in trigonometry and pre-calculus. Now, this is not the unit circle, but it's kind of moving in that direction. So what you see here is part of a circle. It's in the first quadrant. The center is at the origin, and there is 1 point plotted on the circle at 3, 4. And what we're going to do today is this. We're going to take this point and we're going to draw a radius from the origin to that point. Okay, we're going to draw a radius like that. Okay, so if you're taking notes on this, what you're going to see is going to happen is we're going to make a triangle. And if you just draw the triangle, that's good enough. So we've got, here's the radius, and then we're going to drop a vertical line straight down. And you're going to see that it hits the x-axis at 3, which makes sense because that's our x-coordinate. And we're going to go straight across to graph in the base of the triangle, if you will. So this triangle has a width of 3 units. That's gotten by the x-coordinate, and it has a height of 4 units, which is gotten by the y-coordinate. Okay, that's 4. All right. Now, you know what? Let me erase it and make it a little bit better. I can do better than that. 4. Now, this is called a leg of the right triangle. Remember, there's a right angle here because of how the horizontal and vertical components come together. So we have one leg that's 3 units of length, one leg that's 4 units of length, and the hypotenuse is unknown. But we can find it using the Pythagorean Theorem. Since it's a right triangle, a squared plus b squared equals c squared. So a and b can be either leg, it doesn't matter. So we're going to do 3 squared plus 4 squared equals c squared. 3 squared means 3 times 3, which is 9. 4 squared means 4 times 4, which is 16. That equals c squared. You guys should be familiar with this from geometry. 9 plus 16 is 25 equals c squared. Take the square root of both sides. C equals 25 is a perfect square because 5 times 5 gives you 25. So the square root of 25 is just 5. We can put that into the picture. Not only is this length 5 the radius of the circle, but it's also the hypotenuse of the triangle. So the next thing I'm going to ask you to do with this, now that the triangle is all built, and again, if all you have on your paper is this triangle with 3, 4, 5, you're cool. Now, the next thing we're going to put in is there's an angle here that we're going to call theta. It kind of looks like a circle with a little squiggle through it. That is called theta. It means an unknown angle. That goes right here by the origin. And now what we're going to do is we're going to figure out, starting here as our reference angle, what is the sine of theta, the cosine of theta, and the tangent function from theta. Remember our little jingle, SOHCAHTOA. Okay, this should help us. So if you put your pencil in your brain right here, sine means opposite over hypotenuse. So from here, the opposite is 4 and the hypotenuse is 5. That's your sine ratio. Done. That's all you need to do. Cosine is a little funky word for adjacent over hypotenuse. So I'll write that down. Remember, the adjacent connects your reference angle to the 90-degree corner. So your adjacent here is 3, and your hypotenuse is still 5. Okay, and last one. Tangent is a little fancy word for the opposite side over the adjacent. So if you go back to your reference angle, the opposite side goes all the way through to the other side. 4 is your opposite, and the adjacent again connects to the 90-degree corner. That is 3. So this is our first example of a right triangle inscribed in a circle, and we have 1 down and 2 to go. I want you guys to take careful notes on this, so hopefully you'll know what you're doing. Okay, next we have the same scenario, but we have a different point on the circle. Now the point on the circle is 5, 6. So again, from that point, we want to drop straight down and make the vertical component of the triangle. We want to draw the radius, which goes from that point to the origin. And again, you know, I could do, there is a tool here that draws a straight line, but I'm just kind of trying to show what you'll be doing on your paper and pencil. You can use a straight edge or a ruler too, and then connect the base, which is from the origin to right there. Okay, so here is your right triangle. The base is worth 5. Again, you can get that from your x coordinate. The up and down component, or the vertical component, or height, is 6. That's gotten by the y. And the hypotenuse, again, is missing. So we go right back to our good friend Pythagorean Theorem. A squared plus b squared equals c squared. Again, it doesn't matter which one's a and b. It could be either leg. So I'm going to do 5 squared plus 6 squared equals c squared. Crunch those out. 5 squared, 5 times 5 is 25. 6 squared, 6 times 6 is 36, equals c squared. Add 25 plus 36 is 61, equals c squared. Take the square root of both sides, and that is it. You cannot break down the square root of 61. That stays as is, and I do not want you to use a decimal. So this is kind of, you know, a lot of students don't like using square roots. Let's see, 7 times 7 is 49, so this answer is bigger than 7. 8 times 8 is 64, so the length here is a little bit less than 8. If you're thinking about, you know, like a counting number, a little bit less than 8, but we're going to keep it as a square root. So this length is the square root of 61, which is a little bit less than 8. Now, we're going to do the same thing here as we did in the last problem to wrap this up. We're going to figure out what is the sine ratio from theta, and I'll put theta in. It goes right here. It's this acute angle next to the origin. We will figure out the cosine from theta, and we will figure out the tangent ratio from theta. Okay, here we go. Sine means opposite over hypotenuse. So from theta, the opposite is 6, and the hypotenuse is the square root of 61. Now, if you can get this far, cool. But it's a little bit, it's like bad grammar to have a square root in the denominator. So the process to undo that is to multiply top and bottom by that denominator, the square root of 61. So now you have 6 times root 61 is just that, over the square root. Any square root times itself is just the number. Okay, so that would be the best answer. If that totally throws you for a loop and this is the best you can do, this is fine for now also. Cosine is a fancy word for adjacent over hypotenuse. So the adjacent here, remember, it connects the theta to the 90-degree angle. So that's 5. And the hypotenuse is, again, the square root of 61. If this is as far as you can go, cool. But if you can remember to multiply top and bottom by that square root, you get 5 root 61 over 61. That's the best looking answer. And then finally, tangent is a fancy word for the opposite side over the adjacent. It's that ratio. So the opposite here is 6, and the adjacent is 5. Done. So again, you're finding the 3 trig ratios of a right triangle: sine, cosine, and tangent. 2 down, 1 to go. Last but not least, we have one more scenario. We have a new point on the circle. This point is at 3, 3. So I will take this, I will connect it to the origin to have a right triangle. Maybe I can do a little bit better than that. That's better. Drop a height straight down. Oh, that's not so good. Drop a height straight down. That's not too bad. And then the base. Okay, so again, if you're doing this on paper and pencil like I'm asking, you don't even need to really put the circle in. Just draw the triangle and let's label it. We have the base is 3 units. Again, that comes from your x. The height is 3 units. That comes from your y. I'm going to put in theta, but unfortunately, we don't need the hypotenuse, so you can kind of imagine where this is going. We're going right back to good old Pythagorean Theorem. So we've got 3 squared plus 3 squared equals c squared. Crunch it out. 3 squared, 3 times 3 is 9, plus another 3 times 3 is 9 equals c squared. 9 plus 9 is 18 equals c squared. And to undo the squared, you take the square root of both sides. So you get c equals the square root of 18. Now, if this is as far as you're comfortable going, let's do the best we can here. That's not bad. But if you remember the rules for breaking down a square root, if the number inside of the square root is divisible by one of the perfect square numbers, like 2 times 2 is 4, or 3 times 3 is 9, or 4 times 4 is 16, you divide it out. You may notice that 18 is divisible by 9. So I'm going to say, hey, you weasel, you square root of 18, you're nothing more than the square root of 9 times what? 9 times what gives you 18? 2. So then I go a step further and I say, okay, square root of 9, you're a perfect square. The square root of 9 is a whole 3, and then the root 2 is the leftovers. So that's the best answer here. C is worth 3 root 2. If that knocks you for a tizzy, if you can at least do Pythagoras and root 18, you'll be cool. All right, now to take this one home, what do you think I'm going to ask for? I'm going to ask for, what is the sine from theta? What is the cosine from theta? And what is the tangent ratio from theta? Well, let's do them one at a time. Oh, and by the way, let me put in that c value, that length of 3 root 2. That goes right here. That is the hypotenuse. So we've got hypotenuse, opposite, adjacent. Well, let's do it. Sine, that doggone fancy word for opposite over hypotenuse. So specifically, what do we have? We have 3 over 3 root 2. Now, if this is as far as you can take it, not bad. But we can try to get rid of that square root, also called the radical. You multiply top and bottom of the fraction by it, the square root, root 2 in this case. So now we have 3 times square root of 2 is 3 root 2 over 3 root 2 times an additional root 2. Well, root 2 times root 2 is a whole 2 times the 3 would give us 6. Now, don't shoot me, I'm just a messenger. You can simplify this one little bit more. 3 goes into itself, 3 goes into 6 twice. So the final answer for the sine ratio is square root of 2 over 2. That is the sine ratio for this triangle. Cosine is a fancy word again for adjacent over hypotenuse. So we have the adjacent here is also 3. The hypotenuse is 3 root 2. Huh. It's the same thing as we just had. Why would that be? Well, the opposite and the adjacent are the same. They're both 3. So of course, if that's the situation, the sine and the cosine will be the same. So we already know where this is going. The final answer is going to be root 2 over 2 because we're working with the same numbers we did in the previous example. So cosine's done. So that leaves us with tangent. Tangent, opposite over adjacent. So we have the opposite's 3. The adjacent is 3. And hey, that one's not bad to simplify. Anything divided by itself is 1. So, for tangent, you can get 1. And, for somebody who's really paying attention, you might be able to figure out what this unknown theta, this angle is. Any triangle that has the adjacent leg and the opposite leg are the same, that's 45 degrees because this is coming from a square. Okay, 45 degrees. So there is our continuity learning plan, lesson number 2, working more with sine, cosine, and tangent of a circle with a triangle inscribed in it. Hopefully this was helpful. The nice thing about the video is you can watch it again. You can rewind if you need more help. So at this point, you can move on to your assignment. There are 4 examples that are very similar to this. And if you have a printer, cool. If not, paper and pencil. Snap a pic of it, upload it to Google Classroom. If you need any help, email me. I look forward to you guys turning in some more great work. This lesson is very instrumental in your development, especially if you want to take pre-calculus next year. Thank you very much. Good luck. Let me know if you need my help, and have a great day.